Hi everyone, my name is Dr. Naga Malleswari, Assistant Professor, Department of Mathematics from VIGNAna JYOTHI Institute of Engineering and Technology, Hyderabad. Today I am here to discuss about the topic inverse Laplace transform, and this topic is part of your course Ordinary Differential Equations and Vector Calculus. Laplace transform helps us to convert a function from time domain to frequency domain, where solving equations becomes much easier. But once we solve a problem in frequency domain, we need to bring the solution back to time domain. This reverse process is called inverse Laplace transform. Let us begin with the definition of inverse Laplace transform. Laplace transform of a function f of t is f of s. Then f of t is called inverse Laplace transform of f of s. That is L of f of t is equal to f of s. Then inverse Laplace transform of f of s. F of t is equal to L inverse of f of s. So it can be written as L inverse of f of s is equal to f of t. Here L inverse is called inverse Laplace transform operator. Inverse Laplace transform converts frequency based function f of s into time based function f of t. Now we discuss inverse Laplace transform of some elementary functions. We are taking the basic elementary functions like constants, exponents, sine and cosine functions that have been already transformed by using Laplace transform. Now we are finding their original time based functions by applying inverse Laplace transform. F of s is equal to 1 by s. We have to find out inverse Laplace transform of 1 by s. L inverse of 1 by s is equal to constant 1. That is inverse Laplace transform of 1 by s is constant function 1. Next, f of s is 1 by s square. We have to find out inverse Laplace transform of 1 by s square. L inverse of 1 by s square is equal to t. Inverse Laplace transform of 1 by s square is a function t. Similarly, we get inverse Laplace transform of 1 by s power n plus 1 is t power n by n factorial. Inverse Laplace transform of 1 by s minus a is exponential function e power at. Inverse Laplace transform of 1 by s plus a is e power minus at. Inverse Laplace transform of 1 by s square plus a square is 1 by a into sine at. Inverse Laplace transform of s by s square plus a square is cos at. Inverse Laplace transform of 1 by s square minus a square is 1 by a into sine hat. Similarly, we get inverse Laplace transform of s by s square minus a square is cos hat. These are some standard formulas of inverse Laplace transform. Following these formulas are followed by previous one only. For example, inverse Laplace transform of 1 by s plus a whole square plus b square is equal to, here s plus a is there, we have to take it outside of inverse Laplace transform, then we get e power minus at into L inverse of 1 by s square plus b square, that equal to e power minus at. L inverse of 1 by s square plus b square is 1 by b into sine bt. Now we discuss the properties of inverse Laplace transform. First property is linearity property. Let f1 of s and f2 of s are Laplace transforms of f1 of t and f2 of t respectively. Then inverse Laplace transform of c1 f1 of s plus c2 f2 of s is equal to c1 L inverse of f1 of s plus c2 L inverse of f2 of s. Here c1 and c2 are constants. That means inverse Laplace transform of linear combination of a function is equal to linear combination of individual inverse functions. Here linear combination is C1 F1 of S plus C2 F2 of S. Individual functions are L inverse of F1 of S and L inverse of F2 of S. C1 and C2 are constants. We have to prove this linearity property theorem. We have first take linear combination C1 F1 of t plus C2 F2 of t. Apply Laplace transform to this. Laplace transform of C1 F1 of t plus C2 F2 of t is equal to C1 Laplace transform of F1 of t plus C2 Laplace transform of F2 of t. Laplace transform of a function is f of s. Substitute in place of L of f1 of t, C1 f1 of s plus C2 f2 of s. Therefore, C1 f1 of t plus C2 f2 of t is equal to inverse Laplace transform of C1 f1 of s plus C2 f2 of s, which is equal to inverse Laplace transform of C1 f1 of s plus inverse Laplace transform of C2 f2 of s. C1 and C2 are the constants. Take C1 outside of inverse Laplace transform. C1 L inverse of f1 of s plus C2 L inverse of f2 of s. This property we call it as linearity property of inverse Laplace transforms. Now we discuss example problem for better understanding of linearity property. Find L inverse of 2s minus 5 by s square minus 4. L inverse of f of s is given here. We have to find out f of t value. Let f of s is equal to 2s minus 5 by s square minus 4. Apply inverse Laplace transform to this. L inverse of f of s is equal to L inverse of 2s minus 5 by s square minus 4. That equal to, apply linearity property here, L inverse of 2s by s square minus 4 minus L inverse of 5 by s square minus 4. That equal to, here 2 is constant, take it outside of inverse Laplace transform, 2 into L inverse of s by, and denominator which can be written as s square minus 2 square minus 5 is constant, 5 into L inverse of 1 by s square minus 4. That equal to 2 into L inverse of s by s square minus a square. Formula is there. L inverse of s by s square minus a square is cos hat. Here a is 2. Cos h a is 2 into t minus 5 into L inverse of 1 by s square minus a square. Here 4, we can write it as 2 square in denominator. Then we get 5 into 1 by a sin hat. A is 2. 1 by 2 sin h 2t. Therefore, L inverse of 2s minus 5 by s square minus 4 is equal to 2 cos h 2t minus 5 by 2 sin h 2t. See another example. Find inverse Laplace transform of 1 by s into s plus 1 s plus 2. L inverse of f of s is given. We have to find out the value of f of t. First note down f of s value. Let f of s is equal to 1 by s into s plus 1 s plus 2. First we have to resolve it into partial fractions. Resolve into partial fractions. 1 by s into s plus 1 s plus 2 equal to a by s plus b by s plus 1 plus c by s plus 2. We call it as equation 1. 1 by s into s plus 1 s plus 2 is equal to, first take LCM, s into s plus 1 s plus 2 a into s plus 1 s plus 2 plus b s into s plus 2 plus c s into s plus 1. Cancel denominator. 1 is equal to a s plus 1 s plus 2 plus b s into s plus 2 plus c s into s plus 1. We call it as equation 2. First, put s is equal to 0 in equation 2. We have one is equal to a into s is 0. 1 into 2 plus b into 0 plus c into 0. That implies a is equal to 1 by 2. Next, put s is equal to minus 1, because s plus 1 is equal to 0, then s is equal to minus 1. S equal to minus 1 in equation 2. We have 1 is equal to a into 0 plus b into minus 1 plus 2. In place of s we are replacing, plus c into 0. 1 is equal to b into minus 1 plus 1. That implies b value is minus 1. Next, s plus 2 is 0. We get s is minus 2. Put s is equal to minus 2 in equation 2. 1 is equal to a into 0 plus b into 0 plus c into minus 2 plus 1. 1 is equal to c into minus 2 minus 1. C value is 1 by 2 on simplification. Next, we get a is 1 by 2, b value is minus 1, c is 1 by 2. Substituting a, b and c values in equation 1. we get equation 1 is 1 by s into s plus 1 s plus 2, which is equal to a by s plus b by s plus 1 plus c by s plus 2. Now we are substituting ABC values here. 1 by s into s plus 1 s plus 2 is equal to a is 1 by 2, 1 by 2s plus b is minus 1, minus 1 by s plus 1, c is 1 by 2, 1 by 2 into s plus 2. Apply inverse Laplace transform. Inverse Laplace transform of 1 by s into s plus 1 s plus 2 is equal to L inverse of 1 by 2s plus L inverse of minus 1 by s plus 1 plus L inverse of 1 by 2 into s plus 2, that equal to 1 by 2 is constant, 1 by 2 into L inverse of 1 by s minus L inverse of 1 by s plus 1 plus 1 by 2 is constant, 1 by 2 into L inverse of 1 by s plus 2. Equal to 1 by 2 into L inverse of 1 by s is 1 minus L inverse of 1 by s plus 1 is e power minus t plus 1 by 2 L inverse of 1 by s plus 2 is e power minus 2t. Take 1 by 2 common. 1 by 2 into 1 minus 2 e power minus t plus e power minus 2t, that equal to 1 by 2 into, and this whole expansion which is equivalent to 1 minus e power minus t whole square. Therefore, L inverse of inverse Laplace transform of 1 by s into s plus 1 s plus 2 is equal to f of t. What is f of t here? We get 1 by 2 1 minus e power minus t whole square. See another example. This is also related to linearity property. L inverse of f of s is given. First we have to note down f of s value. Let f of s is equal to s square plus 2s minus 4 by s square plus 9 into s minus 5. Resolve it into partial fractions. Resolve into partial fractions. S square plus 2s minus 4 by s square plus 9 into s minus 5 is equal to a by s minus 5 plus bs plus c by s square plus 9. Here s minus 5 is linear part, so that in numerator we have to take a. S square plus 9 is quadratic part, so that in numerator we are taking bs plus c. Now s square plus 2s minus 4 by s square plus 9 into s minus 5 is equal to, take LCM, s minus 5 s square plus 9 a into S square plus 9 plus BS plus C into S minus 5. Cancel denominator. S square plus 2S minus 4 is equal to A into S square plus 9 plus BS plus C into S minus 5. We call it as, this is equation 2, and here we call it as, this one is equation 1. First, put S is equal to 5 in equation 2. We have S square is there, put S is equal to 5, we get 25 plus 2 into 5, 10 minus 4 is equal to A into 25 plus 9 plus BS plus C into 0. 25 plus 10 minus 4, we get 31 equal to A into 34. That implies A is equal to 31 by 34. Now, from equation 2, so what is equation 2? S square plus 2S minus 4 is equal to A into S square plus 9 plus BS plus C into S minus 5. S square plus 2S minus 4 equal to A into S square plus 9A plus BS square minus 5BS plus CS minus 5C. Take S square common, we get A plus B into S square. Next, take S terms common, minus 5B plus C into S. Next, remaining constant terms we have to write here, 9A minus 5C. Comparing S square and S coefficients. A plus B is equal to, here S square coefficient is 1, A plus B value is 1. Then B is equal to 1 minus A, that equal to 1 minus 31 by 34, we get 3 by 34 B value. Therefore, B is 3 by 34. Next, we have to find out the value of C. Minus 5B plus C is equal to 2. Minus 5 into B value is 3 by 34 plus C is equal to 2. C equal to 2 plus 15 by 34. We get C equal to 83 by 34. Therefore, what is A? A is 31 by 34. B value is 3 by 34 and C is 83 by 34. Now, substitute A, B and C values in equation 1. S square plus 2s minus 4 by s square plus 9 into s minus 5 is equal to a is 31 by 34, 31 by 34 into s minus 5 plus b value is 3 by 34, c is 83, 3s plus 83 by 34 into s square plus 9. Now apply inverse Laplace transform. L inverse of s square plus 2s minus 4 by s square plus 9 into s minus 5 is equal to L inverse of 31 by 34 into s minus 5 plus L inverse of 3s plus 83 by 34 into s square plus 9 equal to 31 by 34 is constant. 31 by 34 L inverse of 1 by s minus 5 plus L inverse of 3s by 34 into s square plus 9 plus L inverse of 83 by 34 into s square plus 9, which is equal to 31 by 34 L inverse of 1 by s minus 5 plus 3 by 34 L inverse of s by s square plus 9 plus 83 by 34 L inverse of 1 by s square plus 9, that equal to 31 by 34. Inverse Laplace transform of 1 by s minus 5 is e power 5t plus 3 by 34. Inverse Laplace transform of 1 by s square plus 9. S square plus 9, which can be written as s square plus 3 square. This is of the form s square plus a square cos 3t plus 83 by 34 into inverse Laplace transform of 1 by s square plus 9 is 1 by 3 into sin 3t. Therefore, inverse Laplace transform of s square plus 2s minus 4 by s square plus 9 into s minus 5, which is equal to 31 by 34 e power minus 5t plus 3 by 34 cos 3t plus 83 by 34 1 by 3 sin 3t. Now we discuss first shifting theorem or first translation theorem. Inverse Laplace transform of f of s is f of t. Then inverse Laplace transform of f of s minus a is e power at into L inverse of f of s. This can be written as e power at into L inverse of f of s is f of t. Similarly, if inverse Laplace transform of f of s plus a is equal to e power minus at L inverse of f of s or e power minus at into f of t. That means to find out the inverse Laplace transform of f of s minus a multiply inverse Laplace transform of f of s by e power at. See example problem for better understanding of first shifting theorem. Find inverse Laplace transform of 1 by s plus 2 whole square plus 16. L inverse of f of s is given here. First note down f of s value. Let f of s is equal to 1 by s plus 2 whole square plus 16. Apply inverse Laplace transform. L inverse of f of s is equal to L inverse of 1 by s plus 2 whole square plus 16. See here in denominator s plus 2 whole square is there. First take plus 2 outside of inverse Laplace transform. We get e power minus 2t. L inverse of, then the remaining value can be written as s square plus 16. That equal to e power minus 2t inverse Laplace transform of 1 by denominator can be written as s square plus 4 square, which is equal to e power minus 2t inverse Laplace transform of 1 by s square plus a square is 1 by a into sine at. Apply that formula here. We get 1 by 4 into sine 4t. Since inverse Laplace transform of 1 by s square plus a square is 1 by a into sine at. Therefore, inverse Laplace transform of 1 by s plus 2 whole square plus 16 is equal to e power minus 2t by 4 into sine 4t. See another example. This is also related to first shifting theorem. Find inverse Laplace transform of 2s plus 3 by s square plus 2s plus 2. Inverse Laplace transform of f of s is given here. First note down f of s. Let f of s is equal to 2s plus 3 by s square plus 2s plus 2. Apply inverse Laplace transform. L inverse of f of s is equal to L inverse of numerator can be written as 2s plus 2 plus 1 by s square plus 2s plus 1 plus 1. That equal to L inverse of, here take 2 common from these terms, 2 into s plus 1 plus 1 by, and this expansion which is equivalent to s plus 1 whole square plus 1. That equal to, here in numerator s plus 1 is there and denominator s plus 1 is there. First apply first shifting theorem. Take 1 outside of inverse Laplace transform. We get e power minus t L inverse of 2s plus 1 by s square plus 1 equal to e power minus t. Apply linearity property here. L inverse of 2s by s square plus 1 plus L inverse of 1 by s square plus 1. That equal to e power minus t L inverse of 2s by s square plus 1. Here 2 is constant. 2 into L inverse of s by s square plus 1 plus L inverse of 1 by s square plus 1, that equal to e power minus t into 2 inverse Laplace transform of s by s square plus 1 is cos t plus inverse Laplace transform of 1 by s square plus 1 is sin t. Therefore, inverse Laplace transform of 2s plus 3 by s square plus 2s plus 2 equal to e power minus t into 2 cos t plus sin t. Next we discuss second shifting theorem. If inverse Laplace transform of f of s is f of t, then inverse Laplace transform of e power minus as into f of s is equal to g of t, where g of t is equal to f of t minus a if t is greater than a, 0 if t is less than a. That means shifting the argument of inverse Laplace transform by a units, or we can write like this. Inverse Laplace transform of e power minus as into f of s is equal to g of t is f of t minus a if t is greater than a, 0 t is less than a, that equal to f of t minus a into h of t minus a. Here h of t minus a is Heaviside unit step function. H of t minus a is defined as 1 if t greater than a, 0 if t is less than a. See example problem. Find inverse Laplace transform of e power minus 2s by s square plus 4s plus 5. Given inverse Laplace transform of e power minus 2s by s square plus 4s plus 5. This is of the form e power minus as into f of s. Compare this with standard equation. We get a is equal to 2. See here, this is standard equation. L inverse of e power minus as into f of s. We can write like this also. L inverse of e power minus 2s into 1 by s square plus 4s plus 5. E power minus as into f of s. Here a is equal to 2 and f of s value is 1 by s square plus 4s plus 5. First apply inverse Laplace transform. Inverse Laplace transform of f of s is equal to inverse Laplace transform of f of s value is 1 by s square plus 4s plus 5, that equal to L inverse of 1 by denominator, which can be written as s square plus 4s plus 4 plus 1, that equal to L inverse of 1 by s square plus 4s plus 4 is s plus 2 whole square plus 1. Apply first shifting theorem because in denominator s plus 2 is there. Take plus 2 outside of inverse Laplace transform. We get e power minus 2t L inverse of 1 by s square plus 1 by first shifting theorem. by first shifting theorem. Next, that equal to e power minus 2t. L inverse of 1 by s square plus 1 is sin t. This is f of t value. Now apply second shifting theorem. Therefore, by second shifting theorem, L inverse of e power minus 2s by s square plus 4s plus 5 is equal to g of t. So g of t means what we have to take? F of t minus a. If t is greater than a, 0, t is less than a. Here function f of t is e power minus 2 into t minus 2 sin t minus 2. T is greater than 2. 0, t is less than 2. Or we can write e power minus 2 into t minus 2 sin t minus 2 into h of t minus 2. Here h of t minus 2 is Heaviside unit step function. See the example problem. This is also related to second shifting theorem. Find inverse Laplace transform of 3 plus 5s by s square e power 2s. Given, we have to note down given inverse Laplace transform, L inverse of 3 plus 5s by s square e power 2s. Or we can write like this also, L inverse of e power minus 2s into 3 plus 5s by s square. This is of the form L inverse of e power minus as into f of s. Comparing these two, we get a equal to 2 and f of s equal to 3 plus 5s by s square. Apply inverse Laplace transform. L inverse of 3 plus 5s by s square is equal to, apply linearity property here, L inverse of 3 by s square plus L inverse of 5 s by s square. That equal to 3 is constant, 3 into L inverse of 1 by s square plus 5 into L inverse of 1 by s. That equal to 3 into L inverse of 1 by s square is t plus 5 into inverse Laplace transform of 1 by s is constant 1. 3t plus 5. Next, Apply second shifting theorem. Therefore, by second shifting theorem, L inverse of e power minus as into f of s is equal to g of t. Here 3t plus 5 is function f of t value. L inverse of e power minus 2s into 3 plus 5s by s square is equal to, function is 3t plus 5. 3 into t minus 2 plus 5 if t is greater than 2. 0 t is less than 2. Or we can write like this also. 3t minus 1 into h of t minus 2, where h of t minus 2 is unit step function. See another property, change of scale property. If Laplace transform of f of t is f of s, then inverse Laplace transform of f of as is 1 by a into f of t by a, where a is positive. So changing s to as in place of Laplace domain, time function is stretched here or compressed. Now we discuss example problem for better understanding of change of scale property. If inverse Laplace transform of s by s square plus 1 whole square is equal to t into sin t by 2, we have to find inverse Laplace transform of 8s by 4s square plus 1 whole square. First we have to note down, given inverse Laplace transform of s by s square plus 1 whole square is equal to t sin t by 2. Apply change of scale property. Writing as for s, we get L inverse of, in place of s we are taking as by as whole square plus 1 whole square equal to one by a into 1 by 2 into t by a sin t by a. In place of s we are taking as. Inverse Laplace transform of as by a square s square plus 1 whole square is equal to t by 2a square into sin t by a. But we have to find out inverse Laplace transform of 8s by 4s square plus 1 whole square. For this, put A is equal to 2. Inverse Laplace transform of 2s by 4s square plus 1 whole square is equal to t by 8 sine t by 2. But we have to find out inverse Laplace transform of 8s by 4s square plus 1 whole square. Therefore, multiply this with 4, we get L inverse of 8s by 4s square plus 1 whole square equal to 4 into t by 8 sine t by 2, which is equal to t by 2 sine t by 2. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.